standard library Python, generate our PYBs, which are just these concatenated raw code objects. And then from the obfuscated Python, do the same thing for all of the standard library objects that they've got available, and then essentially diff those two, build up a new opcode map, then use that opcode map in your disassembly and decompilation. So it's a few steps, and we're going to, I'll show you the example in 1 second, because obviously packaged in. So pray to the demo gods. So I've created like a silly little test application. It's only PYC distributed, and we'll just use this to exemplify the decompilations. What I've done is this is a standard Python, like normal Python 2.6.2. This is a modified Python that changes the magic and does opcode remapping, so we can see the collisions taking place. So we'll talk about repdb, which is my extension to the debugger in a bit, but we'll just jump into this. Now, I'll pull up my cheat sheet so I don't have to type in and get my paths wrong. So if we set up a new project, we can now see, so we've got the project layout, everything's empty, PYBs are empty, so we're going to generate the reference PYBs, then we're going to generate the obfuscated PYBs, then we're going to collide them, and then we will see that, and the code reproduces, then writes out a brand new opcode.py and opcodes.py. Opcodes.py is what the equivalent that unpyc uses for the decompilation. So if we do gen reference 2.6, we point this at the standard. So you can see there's Python 2.6.2, libpy 2.6. These are all the standard Python library modules, and now we're going to generate a shitload of PYBs from them. So compiling them all up, generating all the PYBs. Okay, so we've generated a ton of PYBs. If we look in our reference PYB, we can see all those there. If we look, show the format of the PYB. So you've seen it's just concatenated code objects. It looks pretty meaningless, but it means that we can collide in like a neutral format. So now we'll do the same for the obfuscated PYBs. So gen obfuscated 2.6. And now, rather than pointing at the standard libraries, the standard library modules, we're pointing at the obfuscated Python's library modules. So we'll generate the PYBs for all of those. Now, it looks like it failed, but that's just all the warnings, the futures warnings. So I promise you it didn't fail quite that bad. As proof, we've got all our obfuscated PYBs here. So now we're going to collide them and remap. And so if we scroll up, so we're just like literally taking all of them and smacking them against each other. And we can see, for import name, it's gone from 107 to 108. The shift that I did in the obfuscated Python was just incrementing the numbers by 1, but it could have been anything. And so now it says we want to write out our new opcode.py, which we do. And so if we look in the libs, we'll see a new opcode.py has been generated. It's remapped by pyREtic, blah, 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 blah. And the same for opcodes.py, which is essentially the same kind of file, but for the unpyc decompiler. So we've collided both streams, remapped them, regenerated our opcode.py, and now we were in a position that we can use a lot of the standard tools because we've we've remapped their opcode remapping. So we'll jump back into the demo, and I'll show you the decompilation later. That wasn't what I meant to do. That's better. So we've talked about the obfuscations, and we talked about how we got around them at the Python layer. Now we're talking about why do we want to decompile in memory rather than statically off disk. Actually, that's better. So we use like in-memory decompilation for all the reasons that we've said, because often you won't be able to actually access the files on disk, either because they're sitting on a different system somewhere, or because all the obfuscation attempts have been placed onto the around the actual data on the disk rather than the data in memory. All the standard Python decompilers require access to the code, to the file objects, and I mentioned earlier that module objects don't have a code object, which is a bit of a pain. So it means that we have to do, we can't do pure decompilation, we have to do reconstruction, which is kind of inferring the source code rather than taking a code object and decompiling it back out through its assembly instructions. We have to poke and prod at objects and make best guesses about what they actually look like. So that's more reconstruction than actual disassembly, decompilation. And this is from the Python documentation. You know, a module object does not have a code. It's for performance reasons, and it makes life far more difficult than it needs to be. So once an object is imported into a run in Python, a module can't be decompiled at the module layer because there's no objects you can decompile. So we have to do the reconstruction. It's kind of like runtime analysis. We prod and poke. We ask a lot of questions about the object. We use a lot of the underlying double underscore attributes to try and work out more about the object. And then we can have a fairly good guess, not perfect in the some cases. 10? Wow. So this kind of, we can pull together different parts of this source code will come from different areas. The stuff within test.func can actually come from the co.code object because it has one. However, the imports and the foo equals 9, the bar, all the attribute assignments can't come from a code object because there's no code object for it to come from. So we have to do a lot of dancing around and reconstruct it. There are some things that we can never be able to reconstruct. As we can see, there's like foo has an initial value of 9, but then foo is changed to 10. At runtime, we're never going to know that that was initially 9. We can only get its current state. Calls to functions like bar, we won't see that bar called testfunc3. We'll see that bar testfunc3 returned value whatever. So we get the returns from functions. But again, this is all at the top layer, and most people don't program the functions at the top layer. So it's not perfect, but for when you're looking for bugs, it's good enough. And that's often what you need. You know, you're looking for areas of code which are going to be good for bugs, and it's good enough. So the pyREtic toolkit, it's pure Python, obviously. And it just came from my need to wanting to not do custom reversing on every single Python application. So it came from laziness. There are 3 main areas. Decompilation and reconstruction. It uses unpyc, but it's extended. It's made it a lot more error tolerant. A lot of decompilers are very brittle. As soon as there's any deviance in the standard bytecode, they'll fall over. So unpyc has been made a lot more robust. All the patches that I've written for unpyc are going to go back to the guy who wrote it, some Russian guy. There's 3 different types of decompilation which we can show. So decompilation in pyREtic is both a traversal, how you get from one object to the next, as well as how you then decompile that object. So, and depending what constraints and what obfuscations are in place, depend on what is the right technique to use. So we can walk the file system, get access to the module object. If we have access to unmarshal, if they haven't removed that, then we can just demarshal that module object and decompile it. Best case scenario, we'll get high quality source code out of it. But we have to have access to the unmarshal. If we don't have access to the unmarshal, then we can walk the file system and do the object decompilation, the in-memory decompilation, and the source reconstruction that we spoke of. Again, we'll lose some of those top layer objects, but it's still pretty good, and we'll see the compare and contrast to them. And if we don't have access to any of the files, so we can't traverse a file system saying there's this file and that file and that file and that file, we can take an object from memory and then look at all the other objects which it's related to and then do the in-memory decompilation on them. So you don't need access to files on disk, but you will only be able to decompile things that are instantiated into memory within the current state. So there's pros and cons to each technique. It depends what obfuscations are in place, but all are available in pyREtic. Well, it's flown off the side. There is, can I shift? The opcode remap, which we've seen, obviously it makes the process of colliding these streams of PYBs a lot easier, puts it into a few commands. And there's re-PDB, which is a superclassed PDB that gives you access to a lot more reverse engineering functionality. Obviously, it was what I was using before to do the opcode remapping. Also had like a lot of stuff that I put in for laziness, allows calling out to create call graphs, etc. So from the runtime, you can see how all the objects are relating to each other in a call graph sense, which can give you a good way of overviewing a project and where to start focusing and putting more time. So there's some future directions. There's loads of work still to be done. Obviously having it in a GUI would be nice. UmpyC is good. I'm not knocking the guy who wrote it, but it's certainly not perfect. It doesn't implement everything. It would be nice to have some kind of, visualized call graph for seeing all the blocks. Double click on a block, and you can get to the source code. And obviously, it's going to be made into an online service, so you can all send me your bugs. So before we hit the conclusions, I'll show you the remapping, conclude, and then we can get out of here. So we've done the remapping. Let's do the decompilation on the files. I'll show you all three types of decompilation, and we can compare the code which is produced and see kind of where it sucks in places and doesn't in others. So this is the first type. If you've got access to an unmarshalling command, you can take the objects from and just unmarshal them out and decompile them after, obviously, the remapping has taken place. So this is the test app that I spoke of. So if we just decompile that, it's all very quick. This goes into the source code and some ridiculously long path. Yay! Right. So we can see this is a good quality decompile. It's got the imports, it's got the top level object, it's got the function calls. This is because we decompiled from an unmarshaled object. So this is good, but only if we've got the unmarshaled object, the unmarshaled capability. If we haven't, then we can do the memory decompile. Go all the way back and then all the way back out again. And you'll see the areas where at the top layer where reconstructions had to be used rather than proper decompilation, you'll see some changes. So you can see there's kind of this long, strange class there, rather than it just being a test class. Obviously, the ordering D, that was the call to the function. We only get the return of its value rather than it being a function. But it's good enough. You can understand the logic of what's going on. And then if we didn't have access to any files on disk and wanted to do everything in memory, we can do the same thing. Rather than obviously applying it to a path, we have to apply it to an actual object. So if we import the test app, you can see it's in the namespace here. So now if we just point this object